So, good morning, guys. Good afternoon. Good evening. So, this is Kemano to starting with inorganic hybridization. Just straight to the point, we'll be solving few questions, finding the hybridization of few compounds. Like, let's start with CH4, C SO42 minus, SF6, CH3, C2H4. Along the way, I may add more. So, like I said in my previous video, we can use this asterisk number, this Z, to give us 1 over 2 into the central atom valency plus monovalent plus negative ion minus positive ion. Are we together? That's how to find the hybridization, the asterisk. We all know that S, that's 1, SP that's 2, SP2 that's 3. When you have 4, that's SP3 hybridized. When you have 5, that's SP3D hybridized, and so on and so forth. Are we together? So now starting from CH4, we want to check the hybridization. And not just that, I'll be telling us how to also get the lone pair, if they are 1 lone pair or no lone pair or 2 lone pair. Now CH4, the Z, the asterisk will give us what? The central atom is carbon. What's the valence of carbon? The electron in the atmosphere of carbon. That's 4 electron plus. Do we have any monovalent in the compound? Yes, that's hydrogen. And we have 4 hydrogen, 1 times 4. Do you have any negative ion attached to the compound? No. So that's plus 0. Do you have any positive ion attached to it? No, that's minus 0. So at the end of the day, it's going to give us 1 over 2 into what? 4 plus what? Plus 4, which is 8 over 2, which is what? 4. What's 4? That's what? sp3 hybridized. So here we have sp3 what? Hybridization or hybridized for CH4. Now, how many lone pair? They may ask you how many lone pair. Now, your asterisk number here, this 4 minus the what's it called now? The bond is having, like, how many, the central atom, how many surround atom is it bonded with? How many surround atom? Now we have H4 surround carbon. We have, if you want to draw the structure here, you have C H H H H. So C is bonded to 4 hydrogen. So we have 4 surround atom that bond to C. So you are going to subtract this 4, your lone pair. Lone pair is equal to that your asterisk minus how many atoms are attached to the central atom. We have 4. Are we together? So it's equal to 0. So that's 0 lone pair. Are we together? So that's how to get it. Now, number 2, SO42 minus. SO42 minus. So we have our Z equals to 1 over 2, open bracket. Now the central atom is sulfur with 6 valence. Plus, do you have any monovalent? No. This oxygen, that's divalent. So our monovalent there is 0. Yeah, times 4, which will still give us 0 because we have oxygen. We don't have issue with that. No need of times 4 since there's no monovalent. Do we have any negative ion? Yes, plus 2. Minus. Do we have any positive ion? No, minus 0. So at the end of the day, we get 8 over 4, which is what? That's 4, which is same thing as what? sp3 hybridized. Now let's check the lone pair. Now the lone pair now is still going to give us something like 4 minus 4, because we have 4 oxygen attached to the central atom, which is what? 0 lone pair. 0 lone pair for SO42 minus. Are we together? So that's that for that. So the next one is SF6. SF6, our Z equals to 1 over 2. Z equals to 1 over 2, open bracket. The central atom is sulfur 6 plus. Do we have any monovalent there? Yes. Fluorine. Halogens are monovalent. They have minus one, minus one, minus one. Are we together? Plus 7 in the outermost shell as the electron, but they need one more to reach their octet structure. So they are still monovalent. Whether plus one like hydrogen or minus one like the halogen, they are both monovalent, regardless of the sign, whether they are positive or negative. We just need monovalent. Now, so we have sulfur here. One, you don't need the sign if they are minus one. Just put the mono to show that they are monovalent. But we have 6 sulfur. Do we have any negative charge? No, plus 0. Do we have any positive charge? No, plus 0. So at the end of the day, we get 6 plus 6. That's 12 over what? Over 2, which is what? 6. No, the fifth one, the fifth one is um sp3d, which is 5. So the next one now we have sp3d square. That one will give us 6. So the hybridization for SF6 now is going to be what? sp3d square. So how do we get the lone pair? Now what do we have here? We have 6. So you subtract it from the surrounding atom. We have 6 fluorine attached to sulfur. So the lone pair now, the lone pair is going to give us 6, the asterisk value minus the total number of the surrounding atom, 6. So which means SF6 has no lone pair, 0 lone pair. So that's that for that. So that's right. SF6 has no lone pair. So let's move to CH3. 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 So this guy is going to give us, our asterisk will give us 1 over 2. The central atom is carbon with 4 valence electron plus. Do we have any monovalent attached to it? Yes, that's hydrogen. And we have 3 hydrogen attached to it. Do you have any negative ion? No. So it remains plus 0 minus 0. So at the end of the day, we get this 1 times 3, 3 plus 4. That's 7 over 2, which is what? 3.5. So now this decimal, no, I told us in my previous voice note that for this formula to work for everything, then you have to know something, because sometimes you won't get a whole number, you will get a decimal number. So should I approximate this to 4 or to 3? So what will determine is this bond. How many hydrogen is attached to carbon? 3 hydrogen. So you are approximating this guy to 3. Like the bond, there is only 3 bond there. See, you have this 3 hydrogen. It's only 3 in 3 dimensions. So you are going to approximate, assuming it's 4. Maybe we have another stuff here. You are approximating to 4. So far there are 3, then you approximate it to 3. So this one give us 3. Are we together? So which one is 3 there? I think that should be sp2 hybridized. So that one is sp2 hybridized. Are we together? So which is what? sp2 hybridized. Now how do we know the lone pair? Like I said, we have 3 here. How many hydrogen? How many bond does it have with hydrogen? 3 bond to 3 hydrogen. So your lone pair will give you 3 minus 3. That means CH3 too has no lone pair. 0 lone pair or no lone pair. 0 lone pair. So that's that for that. So that's one of the things I was saying in my previous voice note, the approximation. Please get it right. Assuming it's 2.5, I got here maybe 5 over 2, and I got 2.5. So I'll check the bond, the atom that are attached to the central atom. I'm going to check them. How many dimensions can I have the bond? If it's in 2 dimensions, that 2.5 I will approximate to 2. But if it's in 3, I will approximate it to 3. Do you get now? Now the next one is C2H4. If you understand this, it will work. It works for everything. But let me not say everything, because in the thousands of things we still have few exceptions. But it works for almost everything. If you know how the structure will look like, the bond, how it's going to look like. So we have C2H4. So now this, you have to reduce this to like empirical formula, the least ratio it can be. So you are going to divide it by 2. So this guy is, so don't, whenever you see something like this, now, if it is C3H4, and you can't divide this again because you'll be having decimal. But this one now you can divide them too, and you can reduce C2H4 to what? CH2. Are we together? CH2. Do you understand? So your central atom will just be C alone. If it is C3H6, you can reduce it to CH2 as well. If it is what's it called now? C2H8, you can reduce it to CH4. And the same hybridize for C2H4 is same thing for CH2. Do we understand? So our central atom here now is what? With 4 valence electron. So we have 2 hydrogen, 1 times 2, plus negative ion is 0, and our positive ion is also 0. So this guy give us 6 over what? Over 2. 6 over 2, which is what? 3. And that's what? sp3 hybridized. sp3 hybridized. sp3 hybridized. So how many lone pair? 3 minus this hydrogen is 2, abi? That's in 2 dimensions. Sure you get. So this guy C2H4 has what? 1 lone pair. 1 lone pair. sp3 hybridized with 1 lone pair. Do we get it? So yeah, that's right. So those are the few things I'll be doing on hybridization. So what's the next thing? Let's me move to electronic configuration. Electronic configuration. Are we together? So please, let me write those. You need to know this pattern very well. This 1s. So far you're having 1 here. Everything up here will not be more than 1. You move to 2s. So far you're having 2 here. Everything up in this line will be 2, will be up to 2. This 2. So you have to add another thing. After s, you know it is SPDF, because some people don't know how to write this thing out. So listen now, SPDF. So the first one, 1s. This is how it will be going. 1, 2, 3, 4, 5, 6 continuously. So the first one is 1. So you only pick s, 1s. The next one, 2. So you pick s and p, 2s. So here you have 2p. Are we together? The next one will be 3. So you pick, since it's 3, you pick SPD, 3s, 3p, 3d. So the next one will be 4. Since it's 4, you pick SPDF, 4s, 4p, 4d, 4f. The next one is 5. Since there are no more than 4, so this one will still give you 5s, 5p, 5d, 5f. Since there are no more than 4, SPDF, they are just 4. Same thing, 6, 4, all those ones. So now this is how you'll be picking them. The arrow go like this. Are we together? This is how you'll be picking them. 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 So whenever you are doing your electronic configuration, 1s first, followed by 2s. After this, followed by 2p, 3s. After 3s, 3p, 4s. Some people will say 3s, 3p, 3d, which is wrong. You are following this arrow. 2p, 3s, then come back to here because the arrow is downward. 3p, 4s. 4s before 3d, 4p, 4s, 4d, 5p, 3d, 4p, 5s, 4d, 5p. It's just very simple. Very simple. There is no problem with electronic configuration. Is one of the simplest this thing in inorganic chemistry. Are we together? So that's that for that. Now let's start with what's the electronic configuration for magnesium, Mg, and Mg2 plus. I'll just do a few things on this. Once you understand this, there's no problem again. So let me just do this. So we know Mg is in number 12. Are we together? So number 12. Now I'm starting with 1s. That will give me 1s2. Though the maximum electron that the s orbital can take is 2 electrons. Though they will spin in opposite direction, but can take 2 electrons. Maximum. The p orbital is 6 electrons, the d orbital 10 electrons, the f orbital 14 electrons. We all know that. So 1s2. After 1s, what's next? 2x. And we are still dealing with s orbital. So 2s. So far as s, it can't take more than 2 electrons. After 2s, 2p, right? So p can take 6, 2p6. So magnesium is in number 12. You have 1s2, 2s2, 2p6. That's 2, 4, 6. That's 10. So we have 2 left. After 2p6 is 3x. So we have 3s2. So this guy is the electronic configuration for Mg. But for Mg2 plus, no, 2 plus means loss of 2 electrons, not gain. In mathematics, plus it means gain, addition. But in chemistry, in this case, it means subtraction. It loses 2 electrons. So that means everything here is equal to 10. So for the one for Mg2 plus, we give you what? 1s2, 2s2, 2p6. I won't waste my time on this, so I'm moving to transition method now. So I will still come back to electronic configuration as far as transition meter is concerned. Are we together? So please, once you understand it, you don't have issue again with this one. So hallelujah. Now, transition meter. So transition meter, they are the meter like in between group one and two. They are in between the metal in group one and two and the other element in group three and to group eight. They are in between group one and two and group three to group eight. They are like bridge transition, like what for you to move from group one and two to group three to eight, you have to the bridge that will take you from group one or group two to group three to either group eight is the transition. They are the transition meter that will transit you. That's why we are called. Is another word is bridge metal. So another word for bridge is transition. Do you understand? That's why, and because they are metals, that's why we call them transition metal. So that's that for that. And for now, what we'll be discussing on those transition metal, they are scandium to zinc, scandium to zinc, scandium, titanium, vanadium, scandium, titanium, vanadium, chromium, manganese, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel. Nickel, copper, and zinc. Those are the transition metals altogether from number 21 to 30. But out of this, actually, those metals, why we call them, okay, one of their characteristic is that those transition metal, number one, let me not say one. Some of their characteristic is that they are paramagnetic. What do you understand by paramagnetic? They are weakly attracted to magnetic field. Not that they are not attracted, they are attracted to it, but not strongly attracted to it. Are we together? Because of one or more unpaired electron that they have. Are we together? So they are paramagnetic. Another thing is that they are what's it called? They have incomplete d orbital. Their d orbital are incompletely filled up. Incompletely. They have incomplete filled d orbital. So, and we have more characteristic like that. So, but out of those 10, we have three, mainly two, which are chromium and copper. That they we study them separately because of their behavior. So we are going to discuss that. And that's even in my previous video. Probably I may touch it now and I may not. So that's that for that. Now, we all know that all these transition metal they have incomplete filled d orbital. Are we together? But copper has a completely filled d orbital. Yeah, copper. For a reason, chromium too is partially filled. So anything that is going to 100 and you get to 50, you are halfway done. So we still consider chromium as partially filled and hence somehow satisfied because it's partially filled. Are we together as far as the d orbital is concerned? So now the electronic configuration for scandium. All those 1s, 2s, 2p, you don't need to rewrite them. You can just start from argon. Argon is in I'm coming close. Yeah, argon is in number 18. Yeah. So if you want to write the electronic configuration for argon, 1s2, 2s2, 2p6, 3s2, 3p6. Are we together? So if you add it 1s2, 2s2, 2p6, 3s2, 3p6 is equal to 18. So after 3p, you are moving to 4s. So whenever you write argon, the next thing will be 4s. So because some people keep on asking, why do we start with 4s after argon? Because if for argon, you have 1s2, 2s2, 2p6, 3s2, 3p6, and that's already 18. So the next is 4s. So instead of writing all those 1s, 2s, 2p, 3s, 3p, you can just write argon, AR, 18. Are we together? Then, how many do we have left to get to scandium? Since scandium is in number 21, after 18, we need 3 more. So this one will give us what? 2s2. Then we have 4s rather, sorry, 4s2 because after argon we move to 4s. Then we have 3D1. So you can do as many as you want as far as this 10 transition meter is concerned. But let me talk about copper. Copper, copper we have argon 18. No, copper is in number 29, right? So we have 11 more. 4s. S can contain 2. Let me write the 2 first. Then this 20. Then we have 3D. This should be 9. But instead of it to follow this pattern, this S will be 1 and this 9 will be what? 10. So copper has completely filled the orbital. Copper and chromium behave this way. Are we together? That's why we study them separately among all these 10 transition metal. They behave the same way. For chromium we have argon 18. Then after argon 18, that we have 4s1 3d5 is partially filled. The d orbital can take 10 electrons. So this is 5 partially filled. So I've done this in my previous voice note. I don't want to waste much time on it. So now moving to the next topic now. Okay, before going to another thing, let me talk about their variable oxidation state. This transition metal, they have variable oxidation states. Are we together? But sometimes we are able to get their oxidation when they form, um, when they combine with other atoms to form complex ion. Are we together? Something like this. Let me give us some examples of those complex ion. I'm sorry. Uh, those complex ion, like I think I have few examples here. I have like FeCO5, CONH36, and PtCN42 minus. I have PT, though this platinum is not part of those 10 that I wrote. Are we together? So, but let's just write it out. PtCN, are we together? PtCN4, 2 minus. Let me add one more. CONH36, Cl3, CONH36, Cl3. So how do we get the oxidation number of platinum here? Are we together? Now you are going to calculate that of Cn first. Let's see. Let's just do something for Cn here. Now, what's the valence electron? We want to check if this guy is neutral or not, or it contains a positive ion or a negative ion. This C, carbon has 4 electrons. Are we together? In its outermost shell, while nitrogen has 5, which is what? 9. Are we together? So that means